A magnitude 7.3 earthquake off southern Mexico on Friday was strong enough to register on seismographs more than 1,000 miles away across the western United States. That distant shudder is harmless. What it points at is not. The rupture landed at the moment California's faults were measured at their highest stress in 1,000 years, while the San Francisco Bay Area has gone strangely, dangerously silent. In the next few minutes, you'll understand why a quake in another country has seismologists staring at the bay, and why that silence is the part that should worry you. On Friday morning, the seafloor off the Pacific coast of southern Mexico moved. A magnitude 7.3 earthquake ruptured near the border region of Mexico and Guatemala along the Middle America Trench, the long subduction zone that runs down the western edge of Mexico and Central America. The first automated reading came in at magnitude 7.4, and within minutes it was refined down to 7.3 as the full seismic record arrived. That small adjustment is not a mistake, and it is not a cover-up. It is what always happens with a large earthquake. The first estimate is a fast guess built from the earliest waves to reach the nearest stations, and the final number is the careful measurement built from the whole waveform once it has crossed the planet and been read by hundreds of instruments. A tenth of a magnitude point sounds trivial, but on this scale, it is the difference between a rushed headline and a settled fact. And getting it right is the entire job of the global seismic network. For the people along that stretch of coast, the number 7.3 is enormous. On the scale seismologists use, every whole step up is not one notch stronger. It is roughly 32 times more energy released. A magnitude 7.3 does not release a little more energy than a magnitude 6. It releases something on the order of tens of megatons of equivalent explosive force, delivered not in an instant, but in the violent slip of a fault that had been locked and loading for a very long time. That energy does not come from anywhere exotic. It is the slow, patient strain of two tectonic plates, stored over decades and dumped in a matter of seconds. And yet, as we will see, the most important story here is not the shaking in Mexico. It is what that shaking reminded a very different coastline it has been quietly ignoring. The way this earthquake broke tells you almost everything about where it happened. According to the United States Geological Survey, this was reverse faulting, thrust faulting, on or near the plate interface. In plain terms, it was a megathrust-style rupture. Picture two tectonic plates locked together, one diving beneath the other. Here, the Cocos plate is sliding underneath the North American plate at a rate of about 76 millimeters per year, moving toward the northeast, roughly the pace your fingernails grow, but carried out by a slab of ocean floor the size of a small sea. In some segments of this arc, the plates converge even faster, closer to 88 millimeters per year, depending on exactly where along the boundary you measure. That motion does not happen smoothly. The two plates catch and grip along their contact, and the strain builds, year after year, decade after decade, until the friction finally loses and the overriding plate lurches up and over the descending slab all at once. That lurch is the earthquake. The rock does not stretch like rubber and then relax. It holds, and then it breaks, releasing in seconds what took a lifetime to accumulate. This is the same category of fault that produces the largest earthquakes on Earth, the great megathrusts of Chile, of Alaska, of Japan. The reason megathrusts sit at the top of the scale is simple geometry. The locked contact between two plates is a vast, continuous surface, and when a big enough patch of it fails at once, there is almost no limit to how much rock can move. Friday's rupture was not one of those monsters. It broke a modest patch, not the whole seam. But it came from the same machinery, and understanding that machinery is the key to understanding why a quake in one country made scientists more than 1,000 miles away go quiet and start watching their instruments. In the roughly 30 minutes after the main shock, the largest aftershock struck, a magnitude 6.0. As of the latest update, that 6.0 is still the biggest of the sequence. Behind it came a crowd of smaller shocks, numerous magnitude 5s, including a 5.2 recorded after midnight rolling into Saturday. To someone watching from the coast, that cascade of aftershocks feels like the ground refusing to settle. To a seismologist, it looks reassuringly ordinary. That word, ordinary, matters here, so let me be precise about it. Aftershocks follow rules that hold up remarkably well across earthquakes all over the world. The biggest aftershock usually lands more than a full magnitude below the main shock, which is exactly where this magnitude 6.0 sits beneath the 7.3. The shocks come fast at first and then thin out over days and weeks in a predictable decay, and for every jump down in magnitude, you get many more events. A single magnitude 6 as the largest aftershock, a scattering of 5s, hundreds of smaller tremors gradually tapering off. This is the signature of a fault settling into a new equilibrium, not the warning sign of a bigger rupture waiting in the wings. What the data supports is more of the same. 1 or 2 additional magnitude 6 aftershocks over the coming days would be completely normal, and there is always some outside chance that the sequence produces an upper 6 as its largest before it fades. The region also registered 2 small foreshocks before the main shock, though in a zone with this much constant background rumbling, 3s and 2s and the occasional 4 on any given day, calling something a foreshock is partly a judgment made in hindsight after you already know the big one came. That is one of the hardest truths in this science. The small quake that turns out to be a foreshock looks identical, in the moment, to the thousands of small quakes that lead to nothing at all. There is no reliable tell. You only learn which one it was after the ground has already answered the question for you. The point is this: the Mexican earthquake, in isolation, is behaving. It is doing precisely what a fault of this size is supposed to do. Every piece of the sequence, the magnitude of the largest aftershock, the rate at which the shocks are decaying, the absence of anything that breaks the pattern, reads as normal. Hold on to that because it is the setup for the twist. A megathrust earthquake under the ocean is exactly the kind that can push water, and this one did trigger a tsunami threat. The Pacific Tsunami Warning Center issued its alerts and then, a short time later, stood them down. A wave was produced, but it was minor, on the order of half a foot above the normal tide. That is a ripple, not a disaster. Nothing damaging came ashore. It is worth pausing on why the tsunami stayed so small, because it tells you something about the rupture itself. A tsunami is not made by shaking. It is made by the seafloor physically lifting or dropping and shoving the entire column of water above it. So the size of the wave depends heavily on how much seabed moves vertically and how much ocean is stacked on top of it. A rupture that stays deeper or that slips more sideways than up, or that simply does not break a large enough patch of seafloor, will displace far less water. Friday's earthquake, for all its energy, did not heave the ocean floor the way a truly tsunami-generating giant does. The warning system, meanwhile, worked exactly as designed. It flagged the risk within minutes because the responsible move is to assume the worst until the water proves otherwise. Then it watched the coastal tide gauges in real time and canceled the alert the moment those gauges confirmed the wave was small. That is not a false alarm. That is a safety system doing precisely its job. But the quiet ocean here is a preview of a larger theme in this story because the most unsettling signal in this entire picture is not something that moved. It is something that has gone still. Before we cross to California, you need to know what this particular stretch of the Middle America Trench is capable of. According to the United States Geological Survey, 7 earthquakes of magnitude 7.0 or larger have struck within 155 miles of Friday's epicenter since 1950. This is not a quiet fault. It is one of the more productive earthquake factories on the planet, and it has a long memory. The largest of those 7 was a magnitude 8.2, which hit the southern extent of this zone in September of 2017. That earthquake was Mexico's largest in a century. It killed 98 people, and it generated a tsunami. Here's the detail that seismologists find genuinely interesting, and it is worth one extra beat. That 2017 magnitude 8.2 was not the same kind of earthquake as Friday's. It was an intraslab event, a normal faulting rupture that tore deep inside the bending Cocos slab, roughly 70 kilometers down, as the plate flexed and cracked under its own descent into the mantle. Friday's earthquake, by contrast, was a thrust on or near the plate interface, the contact surface where the 2 plates are actually locked together. Same trench, 2 completely different ways of failing. One snapped the slab as it bent downward into the earth, like a bar of metal cracking as you bend it. The other lurched along the seam where the plates grind past each other. The reason this distinction matters is scale, and it is memory. The 2017 event proves this segment can produce earthquakes substantially larger than the one we just watched. A magnitude 8.2 releases something close to 30 times the energy of a 7.3. So Friday's rupture is not the ceiling here. It is a reminder of a ceiling that sits much, much higher, and that has been reached inside living memory. Now for the thread that ties this whole story together, and it is a real, physical one, not a metaphor. When that magnitude 7.3 ruptured off Mexico, it sent seismic energy racing outward through the body of the planet. Earthquakes radiate several kinds of waves, but the fastest is the P wave, the primary wave, a pulse of compression that moves through solid rock at several miles per second. That P wave traveled the length of the continent. About an hour later, it registered clearly on a seismograph station up in the Yellowstone region of the western United States. Think about what that means for a moment. An earthquake off the coast of Mexico physically shook the ground beneath the western United States about an hour after it happened, and a sensitive instrument wrote it down as a clean, unmistakable arrival. That is not exotic. Large earthquakes are recorded on instruments all over the world every single time, and reading those distant arrivals is exactly how we locate and measure quakes in the first place. But it is the literal, tangible link between two coastlines that people usually think of as unrelated. The same class of seismographs that felt the Mexican rupture arrive in the western states are the instruments trained day and night on the fault system running underneath California. The Mexico earthquake did not just make news on the west coast, it made a mark on the west coast's needles. There is something almost poetic about where that P-wave landed. It registered on instruments in the Yellowstone region, a place that is itself under constant watch for its own reasons. And those same instruments happened to catch the fingerprint of a rupture from another country arriving under North America. The seismic network that blankets the western United States exists precisely so that no significant ground motion goes unrecorded, from a local microquake to the distant echo of a megathrust half a continent away. On Friday, that network did what it was built to do, and in doing so, it drew a straight line from a fault off Mexico to the ground under California. And that physical arrival is the perfect excuse to ask the question everyone in California quietly asked on Friday: does this mean anything for us? To answer that honestly, you have to understand what California's faults are doing right now, completely independent of anything that happened in Mexico. A study published in the Journal of Geophysical Research, Solid Earth, led by researchers at the University of Bern working with the United States Geological Survey co-author, reconstructed 1,000 years of stress accumulation across the Southern California fault network. Their finding is the reason for the nervous headlines, and it is stark. Segments of the San Andreas Fault and the neighboring San Jacinto Fault are now locked and loaded to their highest stress levels in the past 1,000 years. Let that land properly, not the highest in a decade, not the highest since the last big one, the highest in a millennium. The study zeroed in on a junction called Cajon Pass and described it as an earthquake gate, a place where a rupture can either stall out or punch through and continue running between the two fault systems. That gate is the hinge of the whole scenario. If it is open when a rupture arrives, a joint failure crossing Cajon Pass could reach roughly magnitude 7.4 to 7.8, and it could strike a far larger area than any single fault event, including the Los Angeles basin itself, where millions of people live directly on top of the hazard. The single most stressed piece of the whole reconstruction was the San Bernardino segment of the San Jacinto Fault, carrying a load of about 3.6 megapascals, higher than at any point the researchers could see going back 1,000 years, and above its own previous peak from nearly 50 years ago. A number like 3.6 megapascals means little on its own, but the comparison is the point. This segment is not just highly stressed, it is carrying more stress than it has at any moment the reconstruction can reach. It is sitting at the top of its own 1,000-year record. And a fault does not care about the calendar. It releases when the accumulated stress finally overcomes the friction holding it shut, whether that tipping point arrives tomorrow or in 10 years or in 50. That is why seismologists talk in probabilities and never in dates. The physics tells you a fault is loaded, but it cannot tell you the hour it lets go. Layer on top of that the southern San Andreas, which last produced a great earthquake in 1857, the Fort Tejon event, around magnitude 7.9. That means this segment has been quietly storing strain for roughly 169 years, longer than the average gap between its major ruptures. The plate boundary keeps moving a few centimeters a year whether the fault slips or not, so every year of silence is another year of strain locked into the rock. This is the real story, and the Mexican earthquake is simply the spotlight that swung around and lit it up. So let me answer the question directly, because the internet has already answered it wrongly. Can a magnitude 7.3 off Mexico actually load or trigger the San Andreas from more than 1,000 miles away? The honest scientific answer is no, and understanding why is worth a careful minute, because it is exactly the point where fear and physics part ways. There are two ways one earthquake can influence a distant fault. The first is static stress transfer. When a fault ruptures, it permanently changes the stress on the faults immediately around it, nudging some closer to failure and relaxing others. This is a genuine measured effect, and it is how seismologists map out which nearby faults an earthquake has loaded. But it falls off ferociously fast with distance. It matters within about 1 or 2 fault lengths of the rupture, tens of kilometers, not thousands. At the range from the Middle America Trench to the San Andreas, static stress transfer is effectively zero. There is no wave of pressure creeping up through Central America and into California, no line of falling dominoes. That is simply not how the physics works. The second mechanism is dynamic triggering, the passing shudder of the seismic waves themselves as they roll through a distant fault. This one is real and documented. The 1992 Landers earthquake in California famously set off small quakes hundreds of kilometers away as its waves swept past. But dynamic triggering is weak. It tends to nudge faults that are already critically stressed and full of fluid, like geothermal and volcanic areas, and it typically produces only small events. It can jostle a system that was already sitting at the very edge. It cannot manufacture a great earthquake that was not already coming. So here is the defensible verdict. The Mexican earthquake is not a trigger for the San Andreas. It is a stress test of our attention. It arrived at the exact moment California's faults were independently measured to be at their 1,000-year peak. And it is that measurement, not the rupture off Mexico, that should hold your focus. Which brings us to the strangest and most unnerving part of the whole picture. And it is not a sound at all. It is a silence. While Southern California's faults sit at record stress, the San Francisco Bay Area has gone unusually conspicuously quiet. Over the past 7 days, only a couple of tiny one-point tremors registered there, the kind of microquakes you would only ever know about by reading an instrument. In a fault system that is supposed to be constantly creeping and releasing small quakes, that kind of quiet is not comforting. Seismologists have a name for a stretch of an active fault that has gone still while everything around it moves, a seismic gap. And a seismic gap can be the signature of a locked segment silently accumulating strain that will eventually be released all at once. Look at the geography, and it gets more pointed. There is seismic activity to the north of the bay and activity to the south, but in between there's a gap, a dead zone that halts right around the Santa Cruz Mountains segment of the San Andreas. That is the very same segment that ruptured in the 1989 Loma Prieta earthquake. A magnitude 6.9 that killed dozens, collapsed a freeway, and stopped a World Series. The northern San Andreas above it last broke in the great 1906 San Francisco earthquake, around magnitude 7.9, the disaster that effectively rewrote how the world thinks about earthquakes. On Friday, a small magnitude 3.0 did strike in the Santa Cruz Mountains near Gilroy, sitting right on the plate boundary from which the Hayward and Calaveras faults branch away toward the East Bay. But one small quake does not break a silence like that. And this is the inversion that sits at the heart of today's story. On most of the planet, you watch for the ground to move. On this stretch of the West Coast, the thing to watch is the ground refusing to. The quiet is the warning. So where does this leave us? Off Mexico, the sequence is behaving. Watch for one or possibly two more magnitude 6 aftershocks in the coming days, with a small chance the largest late aftershock climbs into the upper sixes before the whole sequence fades out. If it stays textbook, it will simply decay away. And that is the most likely outcome by a wide margin. This particular earthquake was violent, but it was not anomalous, and it was not a signal that something larger is imminent along that trench in the near term. In California, nothing about Friday changed the physics. The Mexican rupture did not load the San Andreas, and no chain reaction is rolling up the ring of fire toward Los Angeles. The plates in between are mechanically independent, separated by thousands of kilometers of entirely different plate boundaries, and the roughly 120 to 140 magnitude 6 earthquakes the planet produces every single year, about one every 3 days, are the ordinary heartbeat of a restless Earth, not evidence of an awakening. The globe was never quieter in the past. We simply detect and broadcast more of it now. Look at this year's numbers with a cool head and they confirm it. So far, in 2026, the planet has produced 9 earthquakes of magnitude 7 or larger, against a long-term average of about 15 a year, a pace that runs slightly above normal but nowhere near alarming. The largest of them was a magnitude 7.8 in the Philippines the previous month. And there has been no magnitude 8 anywhere on Earth this year at all. The year is running a touch hot, not off the rails. That distinction is exactly the one that fear tends to erase and data tends to restore. What did not change is the part that actually matters. Southern California's faults are still at their highest stress in 1,000 years. The southern San Andreas is still 169 years into its wait. And the Bay Area is still silent. The single most important thing to watch in the weeks ahead is not another distant earthquake. It is whether that Bay Area quiet breaks with a modest release or keeps accumulating towards something that isn't modest at all. Everything here points to vigilance, not panic. Nothing in this picture is a prediction that the big one arrives next week. What it is a case that the West Coast is closer to the end of its cycle than a comfortable public assumes. The earthquake off Mexico was a reminder, delivered on seismographs from the Yellowstone Plateau to the California coast, that the ground we stand on keeps its own schedule. The most useful thing it did was make us look. Now the job is to keep looking, at the fault that is loudest in the record and at the one that has gone completely quiet.